Hello, everyone. Welcome to this talk on accelerating training of transformer models. My name is Karthik. I'm an engineering manager in the Azure AI platform group at Microsoft. My teammate Sherlock is a co-presenter for this talk. He's here with me today. We are in the frameworks group in Azure AI. In this talk, we are going to briefly discuss what ONNX Runtime is and how it integrates with training frameworks to accelerate model training. Then we will look at what contributes to acceleration and other training capabilities. In the last part of the talk, we will talk about performance improvements observed in pre-training and fine-tuning of BERT, GPT-2, and Turing models. We will end the talk with a demo on using ONNX Runtime for accelerated training in Databricks. Let's take a quick look at ONNX and ONNX Runtime first. ORT is the short form for ONNX Runtime, and I have used that short form a lot in this talk. So if you hear me say ORT, know that I mean ONNX Runtime. ONNX is a format for ML models. It stands for Open Neural Network Exchange. It makes ML models portable. ONNX defines a common set of operators, the building blocks of machine learning and deep learning models, and a common file format to enable AI developers to use models with a variety of frameworks, tools, runtimes, and compilers. It enables users to train models using any framework compatible with ONNX. The trained models can then be converted to ONNX and represented in open and interoperable format and can be deployed to any compatible target. For example, a PyTorch model can be exported using torch.onyx.export functionality. ONNX also enables hardware providers to optimize for a single format and offer the best performance on that instead of trying to optimize for many frameworks. ONNX was originally developed and open sourced by Microsoft and Facebook. Now, ONNX format is managed under Linux Foundation's AI Foundation. ONNX specification is a standardized intermediate representation, and it includes schema for operators defining inputs, outputs, attributes, etc. for that operator. What you see in the right side is the visual notation of an operator. It shows general matrix multiplication operator with inputs x, weight, and bias. It also shows attributes alpha and beta of this operator and output y. Using the specification for ops, like the one in the previous slide, a traditional ML or deep learning model can be represented in ONNX format as a graph of computational nodes. Each node can be a built-in or a custom operator. A model represented in ONNX format, like the one in the previous slide, can be accelerated using ONNX Runtime, which is a cross-platform accelerator for training and inferencing. ORT is architected to plug in custom operators, optimizers, and hardware accelerators. ORT is an open source project developed in GitHub. ONNX Runtime was originally built for inferencing. Support for training was introduced earlier this year in May. As a part of that announcement, we shared how ORT can be used to accelerate PyTorch training of transformer models on a multi-node GPU setup. ORT is a core part of ML stack at Microsoft, bringing together innovations from across Microsoft and the industry. There are many natural language processing scenarios like classification, machine translation, question answering, information extraction, summarization, text prediction, etc., that are relevant to different products and services shipped at Microsoft. With ORT's acceleration on transformer models, it is being adopted by many teams within Microsoft. There are also some external partners who are soon going to publish blogs on how ORT helped with their training scenarios. Our current focus is on transformer models. There is nothing inherently limiting in ORT that prevents using it for other types of models. We picked transformer models as the first ones to use with ORT because they are typically orders of magnitude larger than other models, like the ones used in computer vision scenarios. And training transformer models take a very long time, even with transfer learning. Let's see how ORT is used for training. Here you see an illustration of different steps in a training implementation. Whether you are familiar with PyTorch or TensorFlow or some other framework, the outline of the training implementation would look like what is shown here. To accelerate using ORT, few changes are needed to these steps. Specifically, instead of using the model that is defined using the frameworks API directly, an ORT trainer is created first using or is created first using the model and later used in the subsequent steps. ORT trainers train underscore step method encapsulates optimized computation of loss and gradients and weight updates. This is where the ORT acceleration happens, and that is shown here in the slide in the light green box. The rest of the implementation does not change and still leverages the original frameworks API represented in dark green boxes in the slide. With this approach, ORT focuses on optimization of computation and does not replace the framework itself. Since it can be thought of as a backend to a framework, ORT can be the compute engine for graph generated from different frameworks. Let's see what the experience looks like and what happens behind the scenes. Here on the left, there is a simple model training code template in PyTorch that defines the model, instantiates the model, loss, and optimizer, and goes through the train loop. On the right side, you see how ONNX Runtime is used for acceleration. The changes are that the model created using PyTorch is passed to ORT trainer along with other parameters, and the train loop involves simply calling train underscore step method on it. This is the experience that exists in the ORT Python API today, and we are working on an updated version of the API that will further reduce the number of lines of code changes needed to use ORT for acceleration. And that will enable incremental changes in code towards optimizing the training speed using ORT instead of having users do all of the changes upfront. So this is how it works in the background. ORT trainer is a framework-specific adapter that exports model to ONNX and passes GPU buffers created by the framework to ORT training session API. Training session API handles the acceleration of computation through ONNX Runtime in the backend. Training session is framework agnostic, and adapters can be implemented for different frameworks to work with ORT through the training session API. In this slide, you see ORT trainers for PyTorch and TensorFlow in Keras. Let's take a quick look at the capabilities available in ORT for training. We saw earlier that Onyx model is a graph composed of computational nodes. The way ORT works is that it exports the model inferencing graph and uses it as a forward graph for training. ORT then augments the graph with loss function and work backwards to build a gradient or backward graph with gradient operators corresponding to each operator in the forward graph. Then optimizer nodes are added to finish building the entire training graph. ORT acceleration comes from optimizations done to entire computation graph using standard techniques like constant folding and redundant operation elimination. ORT also builds an optimized gradient graph using automatic differentiation. ORT uses the global knowledge of data dependencies in the static graph to optimize memory and compute. Other perf improvement contributors are efficient memory management and optimizations to CUDA kernels. The main aspect to call out on memory efficiency is the way tensor placement in GPUs is optimized in a 2D space of memory and time. Tensor lifespan is predetermined by the execution order, and ORT heavily reuses allocated buffer space. It also minimizes memory fragmentations and could calculate peak memory consumption before running the model. With such aggressive memory efficiency, ORT can run BERT large pre-training with batch size that is twice the size that is possible in PyTorch without ORT acceleration. For GPT-2, PyTorch implementation would result in out-of-memory error in a V100 GPU with 16 GB memory. With ORT, it is possible to run GPT-2 on that GPU without getting out-of-memory error. Next is the kernel optimizations. There are three types of kernel optimizations done in ORT. The first one is opfusion. By reducing the number of ops or kernels, ORT reduces the computation and memory usage because the intermediate activations for each op do not need to be stashed when ops are fused. Zero activation is used in BERT. ORT fused that into one op. Same thing was done with layer norm, bias GLU, bias dropout, matmul div, etc. The second kernel optimization is on reimplementation. ORT optimized some CUDA kernels to make them faster. The last kernel optimization is on eliminating some redundant computations in the kernels. ORT also supports capabilities like deep speed, zero stage one, mixed precision training, and distributed training that help speed up training. Let's double click on these native training capabilities. Here we see a list of capabilities that are natively supported in ORT for training. Some of them are widely used in the industry. For example, mixed precision training, gradient accumulation, and data parallelism modes are commonly used. Some of these capabilities are not necessarily as popular as others, but these innovations from different parts of Microsoft help optimize and scale model training. Mixed precision training helps make training faster and use less memory. It is a commonly used technique. The next one is on distributed training modes. To accommodate large models and data sizes, parallelism is employed. ORT supports three different types of parallelism. They are data parallelism, horizontal parallelism, and pipeline parallelism. Data parallelism is the most common, where every GPU or rank has the same model, but the data used in the batch in each rank is different. Horizontal parallelism involves maintaining the entire training graph in each node or rank, but each of them have only a subset of the weights. Lastly, pipeline parallelism. This involves splitting the model and distributing it across GPUs. For example, BERT large model has 24 layers, and it can be split into 8 stages, each with 3 layers from the model. With these parallelism modes, ORT can help scale model training. The next capability is gradient accumulation, and it is about computing gradients multiple times and average them before updating weights. In training, batch size is the number of samples used to train the model before one weight update. It impacts training accuracy. Optimal size of the batch is optimizer dependent, and it is an hyperparameter for training. However, batch size is limited by the available GPU memory. To accommodate batch sizes bigger than what can be accommodated in the GPU memory, the solution is to employ gradient accumulation and achieve the desired batch size. The next item here is the gradient checkpointing, and it is about reducing memory consumption by discarding activations and recomputing them when they are needed again, instead of keeping them around. This is a trade-off between memory usage and computation cost. Next item is ADASUM, which is a technique published by Microsoft Research that our team has already contributed to and made available in Harvard. This technique does not help with the training speed, but because of the innovative approach to combine gradients, it helps model training converge faster than the approach of averaging gradients. Using it in ORT is just as simple as setting a flag. And the same is true with the next item here, that is deep speed. So deep speed zero optimizer makes it possible to support models that are 10x size of the models that can be trained using PyTorch without ORT acceleration. So these topics are big topics in themselves. So I'm not going to get into details on each of these topics here, but you should be able to look them up and get details on deep speed, ADASUM, and other techniques like gradient checkpointing. The next section covers ORT training recipes available in GitHub for BERT and GPT-2 models, and code snippets from BERT pre-training implementation to show the code updates necessary on a PyTorch trainer code to accelerate using ORT. These are the different training recipes that are available in GitHub. We are working to publish more examples on transformer training like BART or T5. It should be relatively straightforward to take these examples as references and use ORT with any transformer model like the ones published in Hugging Face model repository. One call out here is that Turing model repo here is a private repo, but if you want to use it, you could request for access. You can get details on the Turing model architecture and instructions to access it at msturing.org. The code changes needed for ORT acceleration are shown here in this slide. The first change is shown in the top left section of the slide, and it is called model description, which defines input and output shapes of the model. In the next version of the API, it will be optional, but using it will help with more efficient memory management. On the top right section of the slide, you see ORT trainer options, and it is used for capturing training options like distributed training configuration or the flags to invoke the native capabilities like mixed precision training that we looked at earlier. Model description, optimizer configuration, and trainer configuration are used along with the model itself to create ORT trainer. As a part of the train loop shown in the bottom section of the slide, train_step method on ORT trainer is called to train the model. We will look at the code changes again during the demo on a simpler model training code. Let's look at performance improvements observed in BERT pre-training with ONNX Runtime acceleration. This table compares ORT's performance for phase 1 and 2 of BERT large model with PyTorch perf numbers on NVIDIA DGX2. When 4 DGX2, each with 16 GPUs, were used, the speedup was about 11% in total. That comes from the throughput increase of about 11.3% in phase 1 and 14.6% in phase 2. There was no change in the accuracy metrics between the accelerated and non-accelerated model training. ORT could train with local batch size that is twice the size of the batch size possible in training using PyTorch without ORT. ORT ran at a local batch size of 128 and 16 for phase 1 and 2 respectively, whereas PyTorch ran at batch size of 64 and 8. The effective global batch size was the same in both cases for apples-to-apples comparison. With optimization in memory utilization and computation, ORT can speed up training of transformer models. The actual performance improvements depends on a lot of factors. Based on the models we have trained with ORT and the data used for training, we have seen perf improvement of about 1.2x to 7x on different models covering GPT-2, BERT, Roberta, and Turing. One observation here is that generally perf improvement is better with larger model sizes. Let's head over to a Databricks cluster for the demo on using ONNX Runtime with PyTorch on the cluster. Let's take a look at how to use ONNX Runtime for accelerated training in Databricks. I have a notebook opened here and connected to a Databricks cluster. This notebook has PyTorch code to train a simple sequence-to-sequence model. It is the same implementation available in the tutorial on transformer module in PyTorch, with a slight modification to use Atom optimization instead of SGD. So this is the PyTorch tutorial example that I'm referring to. So if you want more details on this example, you can look at the documentation in that link. The copy of this notebook is available in GitHub at this location mentioned here. This is that location. The same notebook is used in this demo. If you have any feedback or comments, you can leave that in this GitHub repo. Other training recipes to use ONNX Runtime to accelerate pre-training and fine-tuning of BERT and GPT-2 models are available in this location here, and that is this repo. Here you can find details on how to use it with BERT and GPT-2, and also details on the perf improvements one can expect. To run this notebook, the prerequisites are a Databricks cluster with 7.3 LTS ML runtime and a node with V100 GPU. I am using Databricks in Azure, so I am using one of the node types
that has V100 GPU. In this case, specifically, I'm using standard NC6S V3 node in Azure. I've already installed the Python packages needed to run this example in this cluster. These are those packages that are pre-installed in this cluster. It will take about 4 minutes to run the entire notebook. It will train a sequence-to-sequence model for 3 epochs in PyTorch without ONNX Runtime acceleration first, and then train another model using the same hyperparameters but with the acceleration using ONNX Runtime. In the output of the cells below and in the metrics view of the experiment, you can see that the training time is almost reduced by half with the acceleration without any change in the accuracy metrics. I'm going to run the notebook now before we look at individual steps. The first step is to define the model that uses the transformer module in PyTorch. The next few steps are to load the data and methods to create data batches to use in training loop. So these are those cells that does that. We also initialize a few variables and create this method to calculate the loss. That is followed by model instantiation for training without acceleration. So this is where the model is instantiated and the loss function and the optimizers are instantiated as well. Then we have methods for MLflow logging and train and evaluate methods. In the train method, you can see the conditional execution needed for code paths with and without acceleration. And this is where that if-else block, the conditional execution happens. In the acceleration path, this trainer object is used. That is not created yet in this notebook because we are not going to use acceleration in training the first model. Later in this notebook, before training the second model with acceleration, we will create this trainer object. For now, just know that this train step here on trainer encapsulates all of these individual steps that are typically used in training. This is the evaluate method implementation. And finally, we have the train loop implementation in train underscore model method. The last step is to invoke that train underscore model implementation by passing this flag parameter as false, which will not use acceleration during training. There is also this evaluate call that will evaluate the model that is trained in the previous step. The next section of this notebook is on accelerating this training using ONNX Runtime. The only thing that is needed in addition to the code that is already created in the cells above is to create a new model from scratch and create ORT trainer. So a new model is created here, and this ORT trainer, this trainer object that we mentioned earlier, is created. This wraps the model and this thing called model description, which captures the shapes of the inputs and outputs, and also the optimizer configuration and the loss function. With this ORT trainer, we can invoke the same train underscore model method, but with this accelerate flag set to true. This will enable acceleration during training. And as you can see, it takes about 6 milliseconds per batch, unlike the training here that took about 12 milliseconds per batch. So the training time is reduced by half without any impact to the loss and PPL metrics here. We can see that later when we look at the metrics chart. Again, there is another cell here that can be used to evaluate the model trained using ORT acceleration. So let's take a look at the metrics that are generated from the runs that I did earlier in this notebook. This shows the per batch execution time. And as I mentioned, the training time per batch is reduced by half, and the overall training time is also reduced by 40% or 50%. The other metrics, loss and PPL, are captured in these charts, and as you can see, they are the same between the baseline run without acceleration and ONNX runtime based run that includes acceleration. There are a couple of links available in this notebook that cover details on how ORT is able to accelerate the training and what one could expect on training BERT and GPT-2 models. That's the demo of this notebook. Please try it out and leave any questions or comments on the GitHub repo that hosts this notebook.
ONNX Runtime is an open source project. You can use it too to optimize and accelerate model training and see the same benefits that we have seen while training very large transformer models that are used in various Microsoft services like Bing Advertising, Office Productivity Suite, Visual Studio, and others. Thanks for watching this talk. Please rate and review this session. Sherlock and I are happy to take any questions you have now. Thank you.